So we'll cover a case study on the Android operating system. And our goal in this talk is basically just to look at how a particular operating system does some of the things we've learned in our class. So this is the symbol for Android. I don't know if it's supposed to make you want to buy the product. But, and then Google has all the stuff that's inside of it, YouTube, all the Google Earth, all the different apps that run inside of Android. Okay, so we'll cover a little brief history of Android and the activity manager, the architecture of the system, and then threads and states, and then we'll also cover virtual memory, or actually the lack of virtual memory. Okay, so what is Android? Android is, if you've ever used Apple or the two most popular cell phone operating systems, or Apple has its own proprietary one. And then Android is kind of based on Linux. And it runs Android phones. So, you guys Android or Apple users or a mix?
Android.
Android? Anyone Apple?
iOS.
Okay.
Still the Apple.
Okay. Okay, so yeah, and the interface to it is basically you touching the screen. So even though Android is based on Linux, you can't type commands like ls-l and list out all programs in a file. You can only interface with it by touching the screen. So the history of it is, it was a company started out in Northern California where all the computer programmers live in 2003, and then it was acquired by Google. It's never been known what it was acquired for, but it was at least $50 million in cash plus some stock options, which could have made it a lot more. And one of the big differences between Android versus Apple's operating system is it's trying to be open source, that really anybody who could develop code in Java could write apps for it somewhat easily, put them out on the App Store, and you could download them. They could get on your phone quicker. What Apple tends to do is very restrictive in how to develop apps, and they have to be tested by Apple and approved by Apple, and Apple has a very low approval rate. So if you can get your app on Apple's App Store, it's probably been tested very well and won't crash the phone and that kind of stuff. Whereas Google's goal was to have as many apps made as possible, maybe even risk the apps not working on your phone. Could kick off, could deadlock the phone or ask for resources and not give them back, and not be very, tested very well. So a little bit of a difference, but the main focus was, and there was an alliance of, Google and Samsung, Sprint, got together and wanted to have some open standards for Android, so that it would be very easy for the computer science world to create many, many apps for the phone. Okay, so there's the zygote. Has anyone heard this word? It's probably from biology class. What does it mean? Something like
It's meant to be one of the stages. I'm sure birth cycle is not the proper term, but it's meant to be one of the stages from, an egg becoming a child or whatever.
Okay, like it's the very first thing that creates the next thing.
It's,
like
yeah, I know it's,
first
yes, meant to
cell
be
in
like,
one. Okay, so it's kind of good to know the meaning of where it's coming from, but it's basically the thing that creates everything else, right? Something like that in biology. Okay, so basically the zygote is a special process that launches all the applications around the phone. So users request an application launch by tapping on the screen. So you tap on your screen, and then that will kick off an application. The home screen, that's not really the official name for it, but the home screen is the one you do all your touching with. The home screen is the only application that is listening to the on-click. Now this on-click method, it's a method supplied by Android. This is basically like Dijkstra's P function. where basically this is gonna put your process in a wait state, waiting for an event to occur, and when that event occurs, you wake up and you handle it. So the home screen basically goes into a wait state, waiting for somebody to touch the phone. When the phone is touched, it wakes up and handles, so a parameter would have to be created. What, did you swipe left, did you swipe right, what did you do? That would be passed into the on-click. So the handler for the home screen will then bind. So in binding, we were talking about how a port number or an application number on your phone will be assigned for the activity that's going to be run, and that we'll call the activity manager to create the application that's going to run. The activity manager receives requests to start the activity. And the Zygote, which does a fork, so if you remember in Linux, a fork is not where you create a child process like a thread, but you actually split, you make a copy of yourself, which is allowed in Linux. So the Zygote forks itself, you gotta be careful you say that, forks itself, and starts a new virtual machine to run the app. Okay, so it does this via the start via Zygote method, calling that method, which is in the socket library that comes with Android, which Android developed on top of Linux. Okay, so just kind of an overview of the system. We're a good place to start. You power up your phone and your processor starts running. The processor boots up, initializes the RAM, puts basic hardwares in its correct states, jumps to the kernel, and the kernel is where the operating system starts running. The kernel starts initializing some C code, sets up drivers, and runs the init process, and your phone eventually starts up. The init process, which is this last one here, sets environment variables and creates mount points where you can plug devices into the system, and also starts up daemon processes that don't necessarily have a parent. They run independent of a parent, so they can't be killed with that parent. And then that runs, the daemon processes run service manager and a few different processes, but the most important one is the Zygote, which then kicks off the Zygote main function, which is now ready to begin having applications run. So when the Zygote runs, so I guess they drew it this way because they didn't want it to be a long list. They kind of drew it like a circle, the pad. So the Zygote registers the Zygote, the original process that's going to split off or fork off all the applications that are running. And then it preloads all the Java classes Android is based on Java programming language. Preloads the resources, and then does start system service. So the start system service, which also includes starting the activity manager, is where we'll now go into the wait state for a message to come in and say a new application needs to run. If a new application needs to run, the activity manager picks it up and calls start via Zygote, and it just keeps doing a loop like this. And every time it does this, the Zygote will fork, create a new application. All your applications that are running will just keep piling up by calling the fork operation over and over. So this is the kind of the flow of how the whole system works. Like I say, you can't bring up a terminal and start typing commands in. The only way you can start an app is hit the home page, and it'll run through this loop and spit off the new application. Okay. So if you remember when we talked about Linux, we kind of had, at the top level is how the user interacts, with the operating system. So when you buy an Android phone, things like email, your photo gallery, your calendars, calculators, that all comes with your phone. So this will be standard, stock Android applications. And then you can go create your own apps or buy some off the market and basically this top layer is the only way you can communicate with the operating system. The operating system, all of these apps talk directly to Android APIs, application user interfaces. You could also run Java Apache, which would be running like a web service, and then that could also talk to the operating system. So the Android APIs talk directly to system services. So these are also provided by Android, wouldn't be available in Linux. And this is, things that manage how much power you have, how much battery life is left, and so forth. Things related specifically to the phone. And then these would talk to the actual Linux operating system, which is at this lower level, through another layer of interfaces. So yeah, it's just a layering interface until you finally get down to what would be the Linux operating system. Okay, all right, so when we talked about threading, right, we said for an operating system that allows multi-threaded programs to run, that said any application can split off children processes, and they would run independent of each other under the parent's process, right? Those would be called threads. So one of the biggest dangers in a cell phone app would be if you allowed multi-threaded programming. So for example, you could have an application that wants to take a picture. So you start the picture app, which then takes over exclusive use of the camera and exclusive use of the screen. And then maybe if the person doesn't take a picture within 20 seconds or whatever, it could burn out the battery. So then you might think, well, I'd like to create a separate thread that runs a timer, and if it counts to 20 and nobody takes a picture, then that thread will kill the first thread. Right? So there's a danger to doing that on a cell phone if you let programmers write code that kill other threads and kill other processes. You're giving too much freedom, and then someone could download an app and it could delete all your other apps. So a little bit dangerous. So they wanted to have processes can only have one thread as a rule, instead of creating multiple threads like we're allowed to do on Linux. You can only have one thread. And then any task you need to be done, you can't go and code them yourself. They have to be provided by the phone. So you can kill a thread if you want, or you can take over the camera, or you can take over the screen. But those are tasks that can only be provided by the operating system. You couldn't be able to code those up yourself. So they have kind of a policy of one thread on Linux, one thread per process. So yeah, our projector is, this code is all supposed to be in red. We have a black and white projector, so sorry about that. But anyway, so because of the single thread, we have what we call worker threads. Because of the single thread model of Android, it's vital that the responsiveness of the user interface for your applications that do not block on any thread. So it's one of the reasons they're very restrictive about threads is they don't want threads to go into a deadlock. Right? If you remember, we talked about processes going into a deadlock. One thread's waiting for a resource that the other one holds. The other one's waiting for a resource the first one holds, and we have a deadlock. The phone can't detect that process is in a deadlock. So in Java, for example, the on-click process, code for the on-click process, which is the one that would run, that would get your app to start running. We create a new thread, so this is just referring to writing threading code in Java. We create a new thread, which is a runnable. And so remember, we can inherit from thread, or we can interface with runnable to create a thread. We have a public void method called run, and in the public void method called run is where we run our code. And in order to call the run method, but have it run on a separate thread, Java requires that we call the start method. So remember, we said if you call start, start method, which comes in the thread code in Java. This will create a separate thread and then take the code of the run method, the method called run, and it will run that code on the thread, the separate thread. So this would be the code for the on-click. On-click code. Like I said, I wish this was in red. But okay. So the idea to kind of simulate multi-threading is to actually have processes that your thread could kick off. These would be system processes. And they're put in 4 different categories, kind of from most important down to least important. So we have foreground processes, which required for what the user is currently doing. So that would be something that the user can actually see, and is something that the application that the user is mainly running. Visible process does the work that the user is currently aware of. And then a service process is one that is holding a service that has been started with the start service method. The bottom level of processes are the cached ones. These are processes that are currently running. The user hasn't killed them yet, so they haven't been running for a while. So maybe the user wants them running, maybe the user doesn't want them running. And if we ever got to a point where we were running out of room, we have too many processes running at once, and we needed to get rid of some processes, this is where we would look. We'd look at the cache processes, the processes that haven't been running in a while. They're kept in a least recently used. It's actually not. It's something like what's the least recently used would be like where we're time stamping everything, but the not used recently is where we kind of estimating which ones haven't been used in a while. So it's actually more of a not used recently. In other words, a very quick way to get a good estimate on which process hasn't been used in a while. So they're kept in a list like that, and anytime space is needed for more processes, we would kill ones out of the cache processes. Before they get killed, they're able to return any resources they have or close out any applications that they have currently open, and then they'll be removed from the system. Okay, so if you remember when we talked about virtual memory is where if you had an application that was so big it couldn't fit in main memory, we said, well, we have a trick where we can bring in parts of your program in pages, equal-sized pages, and record in the table where the pages are in memory. And we didn't need the whole program. We just needed the part that happens to be running at the moment. So we'd have a virtual table, and it would tell us where all the pages are. And anytime we run an instruction, we could just look in the virtual table where the page is, and then find the offset into the page and run the instruction. So the creators of Android, and this is just a common small device decision that is made. Since we're using flash memory, you can only write to it so many times, and then the memory's no good anymore. So if we did paging, we'd be reading and writing constantly into pages. We'd wear out the main memory. Plus, it would eat up a lot of the battery. So a decision was made to not use virtual memory on the phone. You have to put the whole app in, or nothing. Don't fit, can't run it. And if there's not enough room for the app, we got to make room. We got to take some of the cached apps and remove them. Eventually, you have too many apps that are running at once, and you can't add any more apps. So, since Linux does allow virtual memory, you could override it. This is the default, is that we don't use virtual memory. You just put the whole app in, or it doesn't go in at all. And so that puts kind of a limitation on us. If you're going to write apps, you have to look at how big the memory is on the phone. You can't write an app bigger than the phone, it won't work. But if there was some special case and you needed to use virtual memory, you could. But they just feel that it would be heavy use on the battery to have your program running, and every time you hit a page fault, right? So page fault happens when you're running a program, but the page you're executing out of is not in memory, so you have to go out to the disk drive and bring it in. They don't want to have page fault and moving memory back and forth. Because it'd be, yeah, like a drain on the battery plus would wear out main memory. Point where you'd have to go get replacement RAM. So, you know, it's just like I say, it's an interesting concept. The invention of virtual memory is a great idea. We could run big programs on little machines, and we can run multiple programs on the same machine and only keep the parts that matter. If you hit a page fault, no big deal. You just go out to the disk drive, bring the page in. But since phone apps are, you know, immediate response, they don't want to take the time to go out to the big memory. And it's bad for the phone. But the part of where your application needs to be loaded in, and not every application will be loaded in at address 0. From the virtual point of view, the point of view of the programmer writing the code, your code starts at location 0. Where it gets loaded into main memory of the phone is some different number, and that's still be needing some translation. So they do use the direct memory mapping that we talked about in Linux. You remember when we talked about Linux, we had part of memory was direct map, where applications are directly mapped to storage, and then other ones we had to use virtual tables to access. So they do use that here just to make your programs not have to need a translation. And yeah, like I say, when we had talked about swapping, where you have it, this is where you have an application that's currently running, but you need main memory. You can have the application in its entirety, not just unused pages, in its entirety, swapped out to the hard drive while it's still running. And if later on you went back to the app and hit some button that made it run again, it would then go out to the hard drive and bring it back into main memory to pick up where it left off. So by default, we don't have swapping, but you can have your program swap. You can write your app in such a way that it can swap. Meaning, if your application sat idle for a while, it could be written out to the disk and then still be alive in the system. But by default, we don't have them. Okay. And then, so this is just, you know, specifications of a recently created phone. Right, so anyone have this one? Samsung S7, Galaxy S7.
Was that the one that had all the
That
weird,
exploded.
the battery failure?
I think that was the
No 7.
No, 7?
Note, right? Only the Note was, all right, so this is the one where the battery wasn't exploding, but yeah. So just to give an idea of, you know, specs on a phone, I guess what's kind of interesting to us in the operating systems class is it comes with 4 gig of RAM. So that's 32-bit addressing, right? So a gig is 30 bits. 2 gig, if you double that, you need 1 more bit to double it. 31 bits is for 2 gig, and 32 bits is for 4 gig. So it's using 32-bit addressing. And then the hard drive, you can get anywhere from 32 to 64 gigabytes of hard drive on the phone. And then you can get an SD card if you want to have more storage on your phone. You want to have a lot of pictures or movies. And yeah, so it's somewhat recent that this came out. And so just kind of in summary, it is a limited version of Linux. Limited version because, you know, you can't just log in and start typing away and issuing Linux commands. You can only go through the user interface that Android gives you. And the user interface decides what things you can and cannot use, what parts of the operating systems you can and cannot use. By default, there's no virtual memory, so you can't bring in parts of your app and keep the parts in a virtual table. But you can override that. So if you work at a company like Google, they may want you to know that Android doesn't allow virtual memory, but there's a way around it. They want you to work on how to get around it. If they had an app that actually needed virtual memory. I don't know. Why, anyone think of a reason why a phone app you would want virtual memory?
We're not gonna buy it.
Well, obviously, if it was so big, it can't fit in 4 gig, you'd have no choice. But you'd have to write like an 8 gig app. I don't think any app is that big.
I've yet to see an app that's, I've yet to use an app at least that's like more than like 1.5 gig.
Yeah.
Maybe 2 gig
But even like,
tops.
what's the famous Angry Birds? The still the.
Oh, I'm sure Angry Birds is not, and I sincerely doubt Angry Birds is even a gig.
Okay, right, so, but what I'm saying is, so if for some reason, if this, you know, obviously, technology keeps growing and growing, so these numbers will probably grow over time. But if you ever had an app that was so big it couldn't fit, or even close to this, because you don't want one app to take up half your main memory, so you may have to, at some point, start using virtual memory. And you'd have to then use system calls that override it, allow it to happen, so. Yeah, like I say, so the point of just doing, it's good to know is, you know, this doesn't turn you into an Android developer, but it just gives you an idea of taking concepts we've learned in this class, and saying, if you take these concepts and you put them on this particular system, like a little phone that doesn't have, very limited in what it could do, the designers of the operating system may start restricting what it can do. And that's what, you know, that's kind of what we're talking about in this case.